We've talked a lot about electricity in the course, of course, and that's because electricity is very high quality energy that we can use to do all sorts of things, light our houses, keep our houses cool or warm as the need may arise, power refrigerators, computers, TVs, so many things, and now increasingly can be used for personal transportation. That's been used for mass transit with electric trains for many years in other parts of the world. So electricity is a very, very important part of the overall energy picture, even though the total amount of energy consumed by humans uh, is mostly in forms other than electricity, but we are growing the fraction that is in the form of electricity. And because we can produce electricity from renewable sources of energy, that's a very important development. So this module, we're going to be understanding how electricity works and what some of the storage technologies are for it. So the first couple of slides here just are a review of what is electricity. And you can think of a couple of the terms in electricity. We talk about gravitational potential, which is also referred to as voltage, as an analogous quantity to the height in gravitational potential energy. So just by having this object some height above my hand, it has gravitational potential energy, and by releasing it, that gets converted into kinetic energy. A battery has electric potential energy, and electric generators produce electric potential energy by separating charge and keeping those charges apart. A whole bunch of positive charge over here, a whole bunch of negative charge over here. And if I connect them by a circuit that runs through a TV or an air conditioner, the electric charge can get the positive, excess positive charge that wants to get over to the negative charge over here. It can travel through that circuit and power that device, that computer, TV, air conditioner, or refrigerator. Uh, because we sort of described electricity before we really knew what it was at a subatomic level, we talk about electric charge moving as positive charge moving, but it's actually the negative charges, the electrons, that move. They're the things that are physically moving. It doesn't really matter for our purposes. What matters is an electric potential is the separation of positive and negative charge, and the greater that potential, that means the more charge I've got separated, that's the greater potential I have to drive an electric current through a circuit and power some electrical circuit. So how do we generate electricity? The photovoltaic cells that we talked about in the module on direct solar power generates an electric potential directly from photons of sunlight. All of the other ways that we've talked about generating electricity use a device like the one that's indicated in the figure here, which is a simple mechanical generator where a coil of wire is rotated in the presence of a magnetic field. So these blue and red blocks are indicating two magnets with a north magnetic pole on the left and a south magnetic pole on the right, and this coil of wire in between. And when the wire is moved, because the wire is a conducting material and it has electrons that are easily able to move through that wire in it, when they're moved by the wire rotating in the presence of that magnetic field, the magnetic force causes the electromagnetic force causes those electrons to move through that coil. And what that does when they do is that produces a current that can travel through the circuit that's sketched out here that goes through a light. You can imagine replacing that light with a city and replacing a little hand crank here with a giant turbine that has got superheated steam blowing by it from burning fossil fuel or boiling water from nuclear power plant or a large windmill turning that as well. So that's how we produce electricity. We've talked about energy and power. The quantitatively electrical power is simply a product of the electric potential, the voltage V, and the electric current, which we represent with a symbol I. And the electric current is measured in amps, and that is literally how much charge is flowing through the circuit each second. So the product of potential and current is electrical power, which is, like all power, measured in watts. So volts times amps equals watts, just like newtons times meters per second equals watts. So you can look at any of your electrical devices that you plug in. If you plug them into your household outlet, that's at 110 or 120 volts, and you can see what their power rating is, how much power it takes to power that device. It might be a few watts. If it's a small device, it might be hundreds of watts if it's a heater or a large device. And you could use that to figure out what's the average current that's going through that device. So all of our electricity in our homes just comes from a big circuit where we've got schematically depicted here on the left a power plant. That's a generator like the one we just saw that is producing a voltage, an electric potential difference, a positive and a negative. And we run a big circuit along electric power lines that you'll see all over our city and country. And those wires are run into circuits in your house, and ultimately they're two of the uh, outlets in a particular outlet. Two of the holes are those two lines, and you plug your light bulb into it, and then you're just closing that circuit and letting the power from the power plant run through them. As a practical matter, in all of our the power that we use on the so-called grid that we get from power plants is something called AC, or alternating current. And that means that if we go back to the power plant schematic here, there's not one of these lines that's always positive and the other that's always negative, but they're constantly changing, trading places, which one is positive and which one is negative. In the United States, they do that 60 times a second. In most of the rest of the world, they do that 50 times a second, and that's just based on how the power plants are designed. What that does as a practical matter is it allows us to use a device called a transformer to change the voltage between a high value and a low value. And because energy is conserved and the power is the voltage times the current, if I increase V, the voltage, the current I goes down. And current literally is the flow of electrons through a wire. And so the more electrons I've got flowing through the wire, the more friction I have, the more heat I have, and the more loss of energy I have. So to have an efficient power system, it's nice to have a low current. And so alternating current circuits allow us to run the power lines with a very large number for V and a very small number for I. And then we have a transformer near our homes that changes the V to a smaller number and changes the I to a bigger number to power our devices. Here you can see that, so just to finish that thought on AC, batteries, for example, are DC. There's a positive terminal and a negative terminal. And that positive terminal is always positive, the negative is always negative, and the current always flows in one direction from those batteries. This chart just shows, as I was saying earlier, humans do not get most of their energy from electricity, but we're getting an increasing fraction of our energy is consumed as electricity. You can see that in the inset, 36% of global primary energy is used to produce electricity, but most of that, or a significant fraction of that, is wasted because it is produced in fossil fuel power plants, which are subject to the second law of thermodynamics and cannot be 100% efficient. So more than half of that primary energy is just wasted as heat. And so while we may be using more than a third of our primary energy to produce electricity, in the end, what we consume is only 13 to 14% of the world's primary energy is consumed as electricity. But that fraction is growing. We're at about 14% now. It's following this trend. It's not growing by a huge amount, but it is possible that if we make changes, that would grow to a much larger fraction in the future. And because electricity can be made cleanly, that's a very important development. And the final chart here just shows where different states and countries get their electricity from. So, for example, overall in the world, 2/3 of electricity comes from fossil 11% from nuclear, 17% from hydro, and that other category is where wind and solar are. In California, you can see that solar and wind together are 12%, and fossil fuel is a smaller fraction, only 61%. And in New Hampshire, they've got some nuclear power plants in a relatively small state, so a relatively small electrical need. They are able to get a lot of their electricity from nuclear power. So the balance of these things varies from place to place, and it just shows that you can uh, reduce the dependence on fossil fuels and have a greater fraction of electricity generation from some of these other resources we've talked about.